Okay, great. Well, thanks so much for the invitation. It's really nice to be here virtually, and it's nice to see a lot of friends, at least online, and hopefully I'll see a lot of you in person sometime soon. So yeah, I'm really happy to be here to tell you a little bit about some of the things I've been thinking about with this great group of collaborators, Lam Hui, Ricardo Penco, Lucas Antoni, and Adam Solomon. To sort of set the, oh, and let me also just say at the very beginning, please feel free to interrupt me at any time, ask questions. And I am also acutely aware that my handwriting is not great. So if anything is unclear, please feel free to ask. Okay, so just to sort of set the physics stage, here's sort of an alternative title that I could have given. So here's sort of the physics question that we want to think about. And at its core, the question is, could you stretch a black hole? I don't know, if you're God or something, could you grab it and stretch it? And since it's not like a murder novel or a murder mystery novel or something, I'll tell you the answer right at the beginning. The answer is no. But the interesting thing is really understanding why the answer is no and what's going on. But to sort of set the stage first, I have to sort of tell you what this question even means. And is there a rigorous way in which we can ask this question? Because questions of this type are sort of notoriously slippery in GR because of coordinate stuff. I should also probably motivate why this is an interesting question. Like, why do you care? So I tell you this thing. Is it just a fact, or is there some reason to care about it? And then, most importantly, the thing that we're going to spend most of the time talking about today is mechanically, or in detail, why not? There should be an explanation for this fact, and I'll try to tell you a little bit about that. Okay. And so a more high-level motivation for thinking about this kind of stuff is that we know that black holes are at the same time, it's kind of confusing, but they're like both deeply mysterious objects and extremely simple, both at the same time. So as quantum systems, they hold like deep mysteries. But there's this amazing Chandrasekhar quote where basically what he's saying is, black holes are made out of gravity. And so they're extremely simple because all they really have in their constitution are like space and time. They're built out of the simplest possible things. And a concrete instantiation of this simplicity of black holes is the no-hair theorems tell us that black hole solutions in GR are sort of uniquely described by their mass, charge, and spin. And so in a concrete way, they're sort of simple like elementary particles. Okay. And so from the attitude I'm going to sort of take is like, let's think about black holes as if they were, ordinary everyday objects, and try to understand their properties in the same way that we would want to understand the properties of ordinary everyday objects. And so we want to think a bit about the properties of black holes sort of in the classical sense. And you might ask, okay, why do I care about this? So there are some sort of concrete places where these properties of black holes appear in observational phenomena. So one type of thing you might want to do with a black hole, one way you sort of probe how it behaves, is you hit it with a hammer or something like that and see how it relaxes, or you drop something into it and see how it relaxes back to the Kerr solution. And the properties of the relaxation of black holes are encoded by these quasi-normal modes, which appear in ring down signals that you could see in gravitational waves. The thing that I'm actually going to focus on today are things more like susceptibilities or response coefficients, where you place a black hole in some external environment and ask how it responds to that external environment. And this is no longer an academic question, because these susceptibilities or response coefficients really would appear in sort of waveforms for LISA. And so you could imagine actually measuring these things. Okay, and so here, this gives you some idea of my level of artistic talent. This is meant to be, some artist rendering of this Event Horizon Telescope picture of a black hole. And then this is just a schematic picture of a binary in-spiral. And I'm just trying to get across the point that, we are now at the stage where we can start to really image black holes and learn things about their properties. And asking these types of questions are no longer purely theoretical, but we could imagine hoping to actually measure these things. Okay. So the concrete thing that I want to talk about today is this idea that if you take an object and you put it in a tidal gravitational field, you can ask what will it do? And it's one point I want to get across is that it's sort of the exact analog of what you would do in electromagnetism when you place an object in an electromagnetic background field. in that case, the charges rearrange themselves and induce a polarization of the object. Here, the thing that couples to the gravitational field is mass. And so what happens is, the atoms of this thing sort of literally rearrange themselves in a tidal gravitational field, and the object mechanically deforms. Okay, and in fact, this experiment has been done for us by nature by the presence of the moon. So the moon sources a gravitational field that the Earth sees. The Earth mechanically deforms due to the presence of the moon, and one manifestation of this mechanical deformation we experience as tides. Okay, and in fact, this is where this sort of question was first thought of by this guy Love back in the early 1900s. And he really wanted to quantify how much the Earth deformed due to the presence of the moon. And at the linear level, this deformation is quantified by these so-called Love numbers. So yeah, so there are a million puns related to love. I'm going to resist the urge to make any of them. It's this guy's name, though. That's ultimately why these things are called Love numbers. And basically what we want to do is we want to compute these Love numbers for black holes. And more importantly, we want to understand their properties. So I should say, the actual numerical values for these Love numbers have been known for about 15 years. They were computed long ago in GR. But okay, to spoil the secret, they turn out to vanish. And so the thing we really want to understand is why they turn out to vanish. That's sort of the thing that I am going to talk about today. Okay.
Sorry, Austin, in the analogy with the E and M, so the Love numbers would be what? Kind of like the polarizability of...
Exactly, it'd be like the electric polarizability, let's say, or the magnetic susceptibility. So it would be like if you had an object whose polarizability happened to be
zero. Okay.
Exactly. Okay, yeah, any other questions about sort of this motivational stuff? Okay, fantastic. All right, so here's sort of an outline of what I'm going to tell you about. So I'm going to start by introducing sort of point particle EFT, because that's the formalism in which I want to ask this question. And the reason that I want to ask this question this way is just to sort of sidestep any issues about gauge ambiguities or anything like that. I want sort of a sharp definition of what these response coefficients are. So we'll sort of define them in some effective description of a black hole at large distances. And then in order to actually extract what these coefficients are, we need to match to some UV calculation. And here the UV is just going to be general relativity. So it's going to be, ultimately, we're going to be solving the wave equation in a black hole background. And what we're going to see is that black hole perturbation theory, or the wave equation in black hole backgrounds, have a lot of symmetries which control the structure of solutions. Okay, and then I'll sort of summarize and talk about some vague speculations and lessons learned from this whole story. Okay, good. All right, so let's start with point particle EFT. Okay, so the philosophy is really that everything looks like a point particle if you go far enough away. And it's really true. Like this is, in a literal sense, if you take an object and you go really far away from it, it's going to look like a point in the distance to you. That's, for a reason. That's a concrete manifestation of this general philosophy. So the idea is we're going to treat black holes like ordinary objects in this sense. We're going to try to treat black holes like point particles and construct some effective description of the black hole as observers very far away from it. Okay, so the idea is you have a black hole moving along some world line here with a characteristic size capital R, or it could be at this level any object with a characteristic size capital R. And if I'm an observer way over here at distances much, much larger than the characteristic size of the object, I can write down an effective description of the object where it is modeled as a point particle. So here's just its free then will go to action. And then these ... dots stand for other corrections I would write living on the world line of this particle that capture the internal structure. And typically, these things are some higher derivative terms that live on the world line of the particle, suppressed by the characteristic size of the particle. And what they do is they encode the structure and properties of the object. Okay, and so this is a relatively familiar notion. It's sort of the thing that we do in the multipole expansion. If you go out to infinity and you have some charge distribution far away, if you have kind of not a great electric field detector, all you can really measure is the total amount of charge in the interior of the spacetime. But if you have a slightly better detector, you can start to measure subleading corrections and 1/r, and you start to infer like that the charge distribution has a dipole or a quadrupole or so on, and you can systematically correct your approximation that things are a point particle. And the analog here is that these higher derivative terms are systematically correcting the exact point particle approximation. Okay. Okay, great. So here, yeah, just to, I mean, I really want to draw exactly the analogy that Angelo was asking about. So let's think about sort of a charged particle from this point of view. So here's the world line action of a charged particle. So the idea is I want to have some particle that couples to bulk electromagnetism. So this is just the bulk action for the photon. Here I'm writing just the world line action for a free propagating particle, now in Polyakov form. And then this coupling between the bulk photon and the world line of the particle is just capturing the fact that this particle has some electric charge Q. And then the things that we're going to be interested in today are these possible higher derivative couplings that I can write on the world line, okay? And at this order in derivatives with two derivatives, there are two inequivalent possible contractions that I can write down involving f mu nu. And the other background object I have around is the velocity of the particle. So that's v mu. And so there are just these two inequivalent contractions I can write down. And philosophically, you can think of them as a coupling of the point particle to e squared and b squared. That's roughly speaking what's going on. And these couplings come with some energy scale, which typically is just the size or the characteristic size of the object, or more properly, it should probably be the characteristic energy splitting of the microstates of the object. Okay, and so there are various things, various reasons why this attitude is useful. I mean, a very concrete one that sort of most people know about is that this gives you like a very snappy explanation for why the sky is blue. It's sort of just by power counting, the sky has to be blue. This is the first interaction between the bulk photon and the world line that's quadratic in the photon. And so if you wanted to look at some scattering of electromagnetism off of the oxygen molecules in the sky or something, the cross section is going to scale like frequency to the fourth just by power counting, and that's exactly what you see. That's why you get this blue spectrum from Rayleigh scattering. But the point I want to get across, at its core is that these higher derivative world line couplings are encoding the physical properties of the object. Okay, and so one manifestation of that is they tell you how light scatters off of a point particle, but these things also encode linear response to sort of static external fields. And exactly like Angelo was asking about, the sort of prototype for this type of question is electric polarizability. And so I could ask or imagine doing the following experiment, which is I take some object, it doesn't really matter what it is, and I place it in a static electric field. And what happens typically is that the charges in the object rearrange themselves. And as a consequence of that rearrangement of charges, you induce some subleading electric field that you then read off. So here's just a sort of plot where this should be the r direction, where here we're going to immerse the object in a constant electric field. What's going to happen is that as a consequence of that, the charges in the object will move around. That rearrangement of charges sources a subleading electric field that now scales like 1/r cubed at infinity. And if I have a good enough detector, what I do is I read off the amount of induced electric field, compare it to the magnitude of the electric field that I applied, and I call that ratio the electric polarizability. And so the electric polarizability in this example is this alpha E coefficient. Okay, so this is the prototype for what we want to do. Okay, so you can just compute the dipole polarizability of an object in the effective field theory. So here we're still talking about charged objects, and the reason that we're doing this is it will make the transition to the gravity case extremely simple. So here I'm just again writing the world line effective action of some charged object, where here I'm just grouping together all the point particle terms, which are the minimal coupling to the electric field, and just calling them the point particle. And here I've changed basis a little bit to electric field squared and magnetic field squared. And now the way that we ask this question in the effective field theory is I imagine that there are some sources that I don't have to specify that induce a constant electric field at infinity. And then what I'm going to do is I'm going to solve the equation of motion for the electric field, where now I treat this thing perturbatively, and it will act to linear order in the electric field like a source. Okay, and so here now I'm solving Maxwell's equations, where there's now some effective source where I plug in this background electric field into this E squared operator. That thing appears like some effective source on the right-hand side. And then I can solve for the induced electric field due to the presence of this source. What you find is you get exactly this solution. So as advertised, it has the constant piece, which I applied. And then there's a 1 over r cubed induced piece, which depends on this characteristic length scale and this unknown coefficient C1. And so in the EFT, the polarizability is really just this ratio. And one thing I want to emphasize is that in the EFT, you can't really calculate this object because it depends on this unknown number. And so at the moment, I haven't told you what this particle is. So I can get some universal formula for what its polarizability is, but I sort of need to know the microphysics of this particle in order to know what C1 is. Okay.
Sorry, and the C2 guy, that's just magnetic field, is related to the magnetic field.
Exactly, exactly. Yeah. So I pulled kind of a quick one on you. So this C1 is not the same C1 as before. Some linear combination, but yeah, but C2, the coefficient of the B squared would be, it's the magnetic susceptibility.
Sure. Okay.
Great. Okay. Yeah. So what I want is I want to figure out what C1 is. And of course, the detailed polarizability depends on what C1 is. And to figure it out, what I have to do is I need to match to some microscopic calculation. I have to tell you about the identity of this charged particle. Okay, and so the simplest example, which is sort of the E&M analog of a black hole, which is that you imagine the object is a conducting sphere. And so here the matching calculation is very simple, roughly because you don't need to know what the electric field looks like inside the object, much like you don't need to know what things look like inside the black hole. And so here we imagine doing now just a calculation in E&M, where we apply some external electric field pointing in the x direction. And now we want to just solve the Laplace equation subject to some boundary conditions. And a sort of recurring theme is that the coefficients in the EFT will end up reflecting the boundary conditions that we impose in the ultraviolet theory or in the microscopic theory. And so here the boundary conditions are, of course, the canonical ones that we use in E&M. So I'm demanding that the electric field looks like some particular thing at infinity because that's the thing I've applied. And then the non-trivial boundary condition is really that I demand that the potential vanishes at the surface of the conductor. Okay, so you can go ahead and solve the equation of motion subject to these boundary conditions. What you find is that the electric field in E&M looks like this. And then I can compare the thing I've computed in E&M to the thing that I computed in the EFT. And of course, I've normalized everything correctly so that C1 is really just 1 here. Okay, so that's, we haven't learned a whole lot other than the fact that, by doing microscopic calculation, you can extract what these C coefficients are. And so we want to do the analogous thing for black holes. Okay, any questions at this point about the philosophy? This is, it shouldn't be too mysterious at the moment. Okay, great. All right, so now the question that you can ask is, so I told you this whole story about having a charged particle coupled to electromagnetism, but of course, I want to talk about black holes, and so you can ask, okay, what really changes about the point particle description if the object is a black hole? And I hope I've convinced you that nothing changes. The only thing that changes are the precise values that these coefficients take. But from a long distance EFT point of view, we should think of a black hole as like any other object. And so the actual construction of the EFT does not change. And so for simplicity, I'm going to restrict to the following setting, where I'm going to be talking about, for most of the talk, the world line effective field theory of a black hole coupled to an external scalar particle. Okay, this may seem like an oversimplification, but it turns out that the properties of sort of a scalar external source and that of a spin-2 gravity or a E&M external source are basically identical and can actually be related to each other. But to avoid having to deal with indices and stuff like that, I'm just going to talk about a scalar external particle. And what the question we're going to be asking for most of the talk is, what happens if I put a black hole in some long wavelength, sort of constant scalar background field? Does it induce some sort of scalar deformation of the black hole? But just to emphasize, we could have done everything for an actual honest tidal gravitational field. It will change essentially nothing. Just the equations will be more complicated. So just for the purposes of this being a seminar, I'm going to talk about the simplest possible case. Okay, so here what we need to do to ask this question is we need to write down the world line effective theory that couples the black hole to some scalar external particle. And so the scalar external particle, exactly like in E&M, has some piece that propagates in the bulk spacetime, and then it can have some couplings to the world line of the black hole. So here, this linear coupling would be the type of coupling if the black hole was charged under this scalar field. And then the couplings that we're going to care about today are these couplings that are quadratic in the scalar field. And here, again, just like in E&M, there are various types of couplings that you can write down. You can write down ones that depend on time derivatives or derivatives along the world line velocity of the black hole. And then you can also write down things that depend on derivatives transverse to the world line velocity of the black hole, which are sort of spatial derivatives. And the question I'm going to be asking about is the black hole's static response. So the way that it behaves when I put it in a constant background field. And so the things that we're interested in are these things which depend on spatial derivatives transverse to the world line velocity of the black hole. Okay, and so at every derivative order, you can write down a unique coupling, which basically has L derivatives, symmetrized and with traces removed. And you should think of these as telling you about the Lth multipole response of the black hole. So if I apply a multipole L scalar background field, you can ask, how does the black hole respond to this Lth multipole background field? Okay, and so in practice,
again, here you could have other operators, no? Or I mean, because here you're essentially this is the analog of F squared. Before you could have.
Well, this is actually the analog. Well, okay, these A's, I've been a little bit agnostic about what they mean. I really mean those to be spatial derivatives. So these are the analogs of F squared contracted with the projector transverse to the velocity of the black hole.
Oh, okay.
There are indeed things like which have time derivatives that I could also write down, but those things all vanish if I apply a static.
Got it. Yeah,
So this is the only thing you can write down
in the static.
For static fields.
Okay.
And you're doing Schwarzschild?
Yeah, for now I'm doing Schwarzschild. That's right. So yeah, in general, I would be able to also use the black hole spin, but yeah, I'll comment on Kerr at the end. So again, yeah, just for simplicity, nothing really changes about the Kerr case except the construction is just more complicated. Yeah, okay. But thanks for asking. Okay, so given this EFT, we can, oh, and yeah, so sorry, one other thing I should mention is that, of course, I do have in mind that gravity is around. And so if I'm totally careful, in addition to this scalar, there's also a bulk graviton that couples to the world line of this particle. It just turns out that the way that we're going to do the matching is sort of at leading order in 1/r. And it turns out that these things, at least in 4 dimensions, give the leading contribution in 1/r. But if I wanted to do matching at subleading orders in 1/r, I would have to keep account of the graviton effects. But I'm just dropping them here for simplicity. But of course, you can include them. Okay, so with that all said, in the EFT, we can just do this calculation. So mechanically, how do we do it? We do it the same way that we would have computed the dipole polarizability in E&M. I imagine there are some sources that set up some background static phi profile, where here, if I want to source the Lth multipole, so I want to source this Lth coupling, I set up some background that has x to the L contracted with a traceless symmetric tensor and with some strength that I call phi 0. And then in exactly the same way, to linear order, this thing behaves like a source in the equation of motion for phi. I can then solve for phi, and it will induce some subleading. Oh, sorry, this that should not be an L. That should be an R. And what you find is there's some R to the 1/L plus 1 induced field if you apply some r to the L field. And I'll call the ratio of these two things. So this is like a scalar love number, if you like. Okay, is that clear? So this is sort of how we would do the calculation in the EFT, and what we want to do basically are figure out what these lambdas are, where again, lambda twiddle is hiding some numerical factors, but it's proportional to the lambda that I would put in the EFT. And you might ask why I'm going through all this pain. Like of course you can just do all these calculations in GR, but the reason I'm going through this pain is that this is sort of a manifestly diff invariant object. And so it's clear that the couplings in this world line EFT are well defined and diff invariant. And so it tells you that, these are really physical responses that you could imagine measuring. So that's really the motivation. Okay, good. Okay, yeah, so all right, so let me just say a little bit about naturalness. So in grad school, my advisor told me you should never talk about naturalness in a talk because it will lead to like arguments about naturalness. So I'm going to I guess violate that edict a little bit, but I will try to only say facts, and then you can interpret them through whatever lens you like to think about naturalness. But I should say this is sort of this is at least what got me interested in this question. So it seems important to say a little bit about it. All right, so to again spoil the result, what happens is that for a black hole, so a black hole is a very special object from the perspective of this world line EFT, all of these couplings happen to vanish. And it's much more general than just this scalar world line couplings. It's actually true for all of these responses. So not only do scalar couplings to the world line vanish, but couplings quadratic in the graviton and quadratic in E and M also vanish. And it happens for all multipolar couplings in 4 dimensions. Away from 4 dimensions, not all multipolar couplings vanish. A subset of them do, where precisely this combination happens to be an integer. And you might think that this at least sort of seems like kind of a naturalness puzzle, just for the following reason, that there's no obvious enhanced symmetry from the perspective of the EFT when you set all these couplings to 0. Okay. Depending upon your worldview, that may or may not bother you. It bothered me a little bit. And so it makes it at least reasonable to look for some non-obvious symmetry that happens to be there when you set all these couplings to 0. Okay, so that's at least the philosophical motivation. We want to go looking for a symmetry. And of course, it easily could have been that no such symmetry existed. And in some senses, that would have been a more interesting outcome, because we're sort of in the post-naturalness era or something. And so I don't know, it's just useful to have different ways of thinking about naturalness, or different physical situations where you can apply the logic of naturalness and see where it leads you. But if you don't like or care about naturalness, everything I'm going to tell you is just true, and then you can interpret it how you like. But philosophically, I want to try to get some insight into whether there can be some enhanced symmetries by sort of just looking at the UV story. Okay.
Maybe this is jumping ahead, but can I ask quickly something? Like, so you say that all these love numbers vanish for black holes.
Yes.
Is it known whether you can sort of engineer other matter profiles that would also have vanishing love numbers, all of them?
Yeah, that's a very good question. I think no. For a reason that will be, for a reason I'll try to explain, but I think no. I mean, roughly speaking, what is special about the black hole case is you're setting some boundary condition, which is essentially regularity of the field at the black hole horizon. For any other object, I think you have to realize it's not a black hole before you get to the black hole horizon. And then the natural boundary condition becomes something like regularity. I'm asking
whether you could badly fine tune something. I mean, it's really a question of, there's something vaguely analogous to this, which is that all the multipole moments for Kerr black holes, they also all vanish at large, but at least there are some people who claim that maybe with a lot of fine tuning, it is possible to sort of like mock up Kerr from far away. It's not obvious if it's stable. There's still a lot that isn't known, but they think you can probably at least get started. So that's what I was wondering, whether with some restriction of positive energy or something, so matter that satisfies a null energy condition or something. Is it possible to set up some matter that has all vanishing log numbers?
Yeah, to be honest, I don't know. You're not the first person that's asked me that, but I haven't. Yeah, I mean, I've thought a little bit about it, but I'm not 100% sure how to do it, and I'm not positive whether or not it's possible. Yeah, I don't know.
Okay,
sorry.
Thanks.
But yeah, it's a great question. I don't know. Okay, so let's turn to the UV story and sort of see what's going on there. Okay, and so the UV story here just goes by the name black hole perturbation theory. So that's just sort of a fancy name for solving the wave equation in black hole backgrounds. And so what we want to do is look at black hole perturbation theory and see what the symmetries of it are. And so roughly speaking, what we want to do is we want to match, again, like we did for the E&M example, we want to match the effective field theory calculation that we did to some UV calculation in full GR. And again, for simplicity, let's just start with the Schwarzschild case. And so here, this is just one way of writing the Schwarzschild metric. And what we want to do is we want to look at the wave equation for a scalar field that lives in the Schwarzschild metric. And exactly like what we saw for the conducting sphere, the boundary conditions that we use to solve the wave equation for this scalar field are going to translate into EFT coefficients in the point particle EFT. Okay, and so since I'm interested in static response, I'm going to, from the get-go, take the static limit, although in a little while, I'll talk about how one could relax that assumption. If all I care about are computing the static responses, it's no problem. This has enough information, but you might be interested for other questions moving away from the static limit. So I'll talk about that a little bit later. So in the static limit, I'm also going to go to spherical harmonic space to make my life simpler. So in the static limit, the equation I'm interested in solving is just an ODE. So that's great. And what I need to do is I need to impose some boundary conditions in order to select the correct solution, which I can then use to match to the EFT. Okay, so let's think about this as an ODE. It has three regular singular points. One is sitting at the center of the black hole, so we don't care about that one so much. There's otherwise one at infinity and one at the Schwarzschild radius. And so what we can do is we can just expand the differential equation around each of these singularities and just sort of see how solutions behave. There should be two characteristic fall-offs around each singularity. And so near infinity, the two fall-offs are just r to the L and 1 over r to the L plus 1. And this is exactly the same thing that we would have seen in electromagnetism or in gravity. There's one sort of growing mode, which is the thing that we're going to apply. And then there's some decaying mode, which is the thing that we want to read off. And we call the love number just the ratio of these two things. And then we can go near the black hole horizon, and we can expand there. What we find is there's one solution which is constant as you approach the black hole horizon. That's its leading asymptotic. And then there's one which logarithmically diverges as you approach the black hole horizon. Okay. And so now what we need are just some boundary conditions that tell us what solution we are interested in. And for a black hole, we're going to demand that the solution is regular at the black hole horizon. Now, of course, we could argue about whether this is the right thing to do. I mean, it's motivated roughly by the equivalence principle. You don't want the black hole horizon to be a special place. You shouldn't be able to tell that something physically diverges there. So we're going to impose regularity there. Another way to think about it is that this is sort of the static limit of having some purely ingoing boundary condition at the black hole horizon. It sort of has the idea that things can only fall in and nothing can come out. Okay. And then the other boundary condition is just we're going to choose some normalization for this r to the L piece at infinity. That boundary condition is not particularly important. The one where all the action is happening is that we're imposing that things be regular at the black hole horizon. And so now the problem is like a concrete mathematical question. So I have a solution that its asymptotic expansion near the black hole horizon is pure one fall off. It's pure constant mode. And I just want to, find the connection coefficients to the two asymptotics in the other region. Okay. All right. So you can go ahead and just solve this differential equation. It's not too hard. It's a hypergeometric equation. And the interesting thing is that the relevant solution turns out to be a finite polynomial. Okay, and so the solution, which is regular at the black hole horizon, is actually pure growing mode at infinity. Okay, and so here's, concretely, it's a Legendre polynomial, but it's really a polynomial in R, where it has an R to the L piece, which is again the growing mode that we would apply as our background field, and then it has subleading terms in R, but then it stops at R equals constant, and notably does not have this 1 over R to the L plus 1 induced tail. Okay, and so from this we would already say, okay, this tells us that the ratio of induced fall off to applied fall off is 0, and so that's another way of saying that the love numbers vanish. But here, I mean, to me, this is the sharpest way of saying why this is a puzzle, like from a math point of view, from the UV, which is that I've given you there's some second order ODE, and it happens to have a solution where when you expand it around 2 of its singularities, there's a single fall off, which is a super non-generic behavior. Usually what happens is if you take a solution that has a single fall off and you expand it around a different singularity, you get some admixture of the 2 allowed fall offs. Okay, so to me, this is like the math puzzle. This is the thing that requires some explanation about, at least from a mathematical point of view. There should be something special about this differential equation. Okay, and then this is the thing which, when you match to the EFT, results in the vanishing of love numbers. Okay, so now let me just describe briefly how the matching goes. Sorry, again, this should be an R. So remember, in the EFT, we computed the static response to some long wavelength phi profile. And we saw that if I apply R to the L, what I get is some 1 over R to the L plus 1 with some coefficient that depends on this coupling, and this quadratic world line coupling. And then the thing we just computed is sort of the exact UV field profile. And we can now match this UV field profile to the IR one. And really, these subleading terms are not important for the matching. If I wanted to match those in the EFT, I would have to keep track of graviton effects. But if all I want to do is to match the leading R to the L profile, I'm fine. And I would be able to match the 1 over R to the L plus 1 profile if it were there. But here, it's not here. And so what I infer is that I have to set lambda L to 0 in the EFT in order to reproduce the correct asymptotic behavior. Okay. And what that means is that the black hole static response vanishes, in the sense that these world line non-minimal couplings are 0 in the EFT. Okay, so that's sort of the essential fact. And you could ask, there are obviously objects where these static responses do not vanish. So you can compare the story I just told you to what would happen if you had some more ordinary object like a neutron star, or I don't know, a table or something. And what would happen there is that I would not be applying, or I would not be imposing boundary conditions literally at the Schwarzschild radius, but instead I would be imposing some other boundary condition that the field takes on some value at R equals R, where a capital R is the size of the object. And then what I'll find is that if I expand this solution near infinity, I'll get some admixture of both the growing and decaying mode. And so I would infer some non-zero static response of this object. Okay, and this relates back to Nima's question. Nima is essentially asking, can I pick this value super carefully so that I only get growing mode? Yeah, to be honest, I'm not sure. I don't think so, but it would actually be very nice to prove such a thing. Okay, good. Okay, yeah. So maybe I should ask at this point if there are any questions about the facts, and then we'll try to understand the facts.
So this last comparison you have done with the neutron star, the only difference is that you impose boundary conditions at a value that is larger than the Schwarzschild radius, or also like the metric is different, or
well,
I think it is. No,
so outside the object, the metric is exactly the same, right? So let's imagine a non-spinning neutron star. So it's still described by the Schwarzschild metric outside. So the only difference really is the boundary condition that you impose at the surface of the object. And really what's going on is you should be imposing that like at R equals 0, things are regular, and this forces some boundary condition for you at the surface of the object.
But then, sorry, maybe I have a stupid question, but
yes,
don't you have a natural way of fine-tuning this? Meaning, take the other solution, the one that has some fixed value at Schwarzschild radius, that you know that it will evolve exactly as to a pure R to the L.
Yes.
Can't you take the value that that solution would have at R equal capital R and impose that as boundary? Meaning, this should have a unique solution. Then it should again
take the black hole solution and chop it off later.
Yeah,
right?
exactly,
Yeah.
exactly.
Sure.
But I think you want to come up with some kind of choice of matter or something that justifies that boundary condition. That was the question I was asking before.
Yeah, exactly. Yeah, so I mean, I agree you can do that, but then yeah, you need to fill in the metric inside as something, right?
Yeah, okay.
That's kind of a challenge.
The question is whether you can fill it in with something with sensible matter.
That requires that particular boundary condition, you're saying.
Right.
Yes.
Yeah.
Okay. Exactly. Yeah, because once you have an actual object, it's no longer natural to impose boundary conditions here. The natural thing to do, I mean, the correct thing to do is to impose boundary conditions at the center, or to you solve for the metric of that object, right?
Got it.
Yeah.
Okay.
I mean,
okay.
yeah,
Yes,
there are examples like where people have these black hole mimickers and stuff like these, gravastars or perfect mirrors or stuff like that. In all those cases, the love numbers are non-zero. I don't know of an example where the love numbers are zero, but maybe you can cook up such a thing. Okay. All right, but thanks. Any other questions? Okay, great. All right, so let's try to understand. I mean, to me, this is the puzzle. Like, this is the thing I wanted to understand. So let me try to explain at least how I understand the resolution of that puzzle. And so, roughly speaking, there's like a lot of symmetry here, and you can use these symmetries to connect the solutions in different asymptotic regimes. And so, in order to make the symmetries apparent, let's try to write things in a slightly quantum mechanical kind of language. And so I want to write the equation of motion for the static scalar field in sort of the form of some Hamiltonian acting on phi equals 0, where the Hamiltonian is just this differential operator. And then you can observe that the Hamiltonian can be written as sort of a square of some other operators with some leftover constant piece, where these operators are just defined in this way. They're sort of like, unsurprisingly, kind of like A's and A daggers. And the nice thing about these D operators is that their commutation relations with the Hamiltonian shifts the index of the Hamiltonian. Okay, so for example, pushing DL past the Hamiltonian to the left lowers the index of the Hamiltonian by 1, or alternatively pushing it past to the right raises the index. And the same thing for D minus. And so that tells me, for example, if I have a solution at level L, then if I act with D plus, I generate a solution at level L plus 1. Okay, and this should already sound like supersymmetric quantum mechanics, because that's ultimately what it is. Okay, all right, so roughly speaking, we can use these sort of ladder operators. So what these things do is they map you from solutions at multipole index L to multipole index L plus or minus 1. And these are not actually the symmetries that we're going to directly use in order to restrict solutions, but we can use them to generate, in a simple way, the symmetries that we care about. Roughly speaking, because we're going to realize that at L equals 0, the equation is extremely simple and it has another symmetry. Where at L equals 0, this is the static equation of motion for the scalar, and it's invariant under this following transformation. In an appropriate set of coordinates, like I'll show you in a minute, this is really just a translation in some radial direction. Okay, and now what I'm going to do is I'm just going to use this D plus operator to take that symmetry at level L equals 0 and lift it up to a symmetry at level L. Okay, and so here I'm writing the generator of this translation-like symmetry, which I'll call a horizontal symmetry. So it's like it's supposed to recall the action of a ladder. So there's some D operators that carry you up the rungs of the ladder. And then at each rung, there's a horizontal symmetry, which acts purely at multipole index L. Okay, so at L equals 0, there's this translation-like symmetry, which commutes with the L equals 0 Hamiltonian. And now I can conjugate that thing with these D plus and minus operators to build an object which commutes with the index L Hamiltonian. Okay, and you can check in detail if you take the action for this scalar field, decompose it into spherical harmonic space. These really are symmetries of the action, and so correspondingly, you can derive their associated Noether currents, or you can just realize that you can use the properties of this algebra of D and Q operators to determine that this J object is conserved in the sense that the R derivative of this J object is 0. Okay, so now at every index L, we have a conserved charge. And these conserved charge can be used. It's since it has to be conserved, it tells you some additional information about the solution. Okay, and so we can use these conserved charges to connect, to sort of read off the connection coefficients between the asymptotic expansions of these solutions. And the really non-trivial fact is that this solution that goes like R to the L, or goes like a constant near the horizon, has charge 0. Okay. And this allows you, this is the only solution that has charge 0. And so, the solution that has charge 0 near the horizon has to be connected only to the solution that goes like R to the L. Because the other solution, this 1 over R to the L plus 1 solution, has non-zero charge. Another way of saying it is that that this thing has to at least have some singular piece near the horizon. And so these two solutions have to be connected to each other. You can in fact see that this has to be an admixture of both solutions, because you also know the Wronskian is preserved. So that gives you another condition. Okay, so to me, this is what it means to solve this problem, because at least from the mathematical point of view, I wanted a way of asking a question near the horizon where you say, okay, I'm going to demand things are regular. How do I figure out what the fall off is at infinity without solving the differential equation everywhere in between? That's sort of I don't know, at least to me, that's sort of what it means to have some symmetry that connects the two asymptotic regimes. And this is precisely something that does that. Just by knowing that this J is 0 in both regimes tells you how these two solutions are connected to each other. Okay, let me give you a slightly different perspective on this. Okay, to me, this is actually the most satisfying way of thinking about the problem. But of course, yeah, maybe, yeah, it's a slightly personal thing, I guess. But remember, if I start from this static Klein-Gordon equation, it's defined in terms of the Schwarzschild R coordinate and in multipole space. If I do the following redefinition of the radial direction, then I can recast the differential equation that I'm trying to solve as exactly quantum mechanics at 0 frequency in this Paschal-Teller potential. Okay, and this Paschal-Teller potential is like a famous example in quantum mechanics, which is a potential that supports reflectionless scattering. And roughly speaking, what that means is you have some potential. If you send in a wave from the right and you ask, what is the ratio of transmitted wave to reflected wave, what you find is that there's 0 reflected wave and the wave just gets transmitted through. That's another way of saying, or it's another version of this kind of statement about there being a single asymptotic in two regimes. It's saying you have a wave that's purely left moving on one side of the potential and still purely left moving on the other side of the potential. And so you can really think of this vanishing of love numbers as like a literal 0 frequency analog of reflectionless scattering. And it can actually even be mapped onto this question of quantum mechanics and this special potential. Okay, so for me, that's kind of, first of all, satisfying, but also it's a nice manifestation of sort of the unity of physics. Like, there are a very small number of special equations. And so these two problems that you would not have thought have anything to do with each other actually mathematically are the same. And another attitude or another way to think about these ladder symmetries that I was talking about is that it's known that this Paschal-Teller potential is very special from the perspective of supersymmetric quantum mechanics. It's one of these so-called shape invariant potentials. What that means is that, so notice this thing carries some index L, which for us is the multipole. And it's known that this thing with index L and index L minus 1 or L plus 1 are supersymmetric partner Hamiltonians. And so you can sort of go down the supersymmetric ladder all the way until you get to L equals 0, where there's just no potential. Oops, sorry. And at L equals 0, since there's just no potential, it's very easy to see that things should be reflectionless. And then going back up the ladder to L is basically the action of supersymmetry. And the reflectionless property is preserved under this transformation. Okay, and so you can think of what's going on is that these d plus minuses are really related to the supercharges of this SUSY quantum mechanics problem. And these horizontal symmetries are consequences of the translation invariance of the L equals 0 potential. Okay, and so to me, this is sort of a satisfying explanation of what's going on, at least microscopically. Okay, yeah, maybe I should ask if there are any questions about this microscopic picture, and then I will go back to the EFT picture.
Does the symmetry, is there any way of seeing the symmetry in the EFT? Well, maybe you're going to.
Yeah, great. Excellent
talk
question.
about that.
All right. Yeah, it's like I planted the question. Fantastic. Yes. So, all right, so I have to tell you about this slide real quick, and then we'll talk about the EFT. So first of all, it's useful to try to get some real space way of thinking about the symmetries without talking directly about breaking everything into multipolar space. And so here's just some at least geometric way of thinking about the symmetry, even though this isn't like really the geometry of the problem, but it's one way of understanding where these symmetries are coming from, which is that at 0 frequency, you could just ask, all right, if I don't go to multipolar space, I can write the 0 frequency equation of motion for this scalar as a scalar field living in some geometry. And it turns out this geometry is Euclidean ADS3 in kind of funny coordinates. And so it actually turns out you can relate this vanishing of love numbers to the transparency of odd dimensional de Sitter spaces, because the equations in Euclidean ADS3 and de Sitter are basically the same. But one reason that this is useful is it lets you write down some real space transformation that when you go back to L space turns into these d plus minus operators. So you can really think of this symmetry as being the sort of real space reason that these d plus minus operators exist in harmonic space. Yeah, to be honest, the horizontal symmetries are still a bit mysterious. I don't know how those things act in real space, but at least these sort of vertical ladder symmetries, I understand where they come from in the real space story. And now this is some real space symmetry of a 0 frequency scalar in Schwarzschild. You can literally just check that the omega equals 0 action of a scalar in Schwarzschild has this symmetry. And this symmetry has a well-defined r goes to infinity limit or r Schwarzschild goes to 0 limit, which then you can ask, how does this thing act in the EFT? Because the EFT is really the thing which is defined at infinity. So it should, this symmetry expanded as r goes to infinity should order by order act in the EFT. Okay.
Sorry, Austin, just to make sure that I'm not lost. So before you have multiple currents, right? For J0, J1, JL.
That's right.
Blah,
That's
blah,
right. That's right. Yes.
And how are they generated by this single transformation for phi that you showed now?
Yeah, good. So that's sort of what I was saying. So this guy, if you transform him to YLM space, turns into some combination of these d plus minus operators. So it's really this guy which mixes the various L's, which is not surprising because it's like a boost in Euclidean ADS, right? So it mixes the various YLMs. And then on top of that, there's another special thing, which is that at L equals 0, there's another symmetry. And then the combination of that symmetry and this guy in YLM space leads to these J's. To be honest, I don't know how to write that other symmetry in real space. Okay.
Right.
So it's this thing plus another symmetry that's responsible for this full structure. But this thing is what's responsible for these d plus minuses. Okay,
let me see if I can recall this. If I start from a phi that is, say, purely r to the L, right? And I apply this kind of transformation, do I generate the other fall off or it stays the same?
Oh, if you act with this guy?
Yeah.
Well, this guy is going to map you between different L's. So I think what you want to ask is if I act with one of these Q's, will I generate the other fall off?
Right.
Right. And if you start with the r to the L guy, you will not. But if you act on the 1 over r to the L plus 1, you will.
Yeah. Okay, got it.
If you like, the r to the L, I guess preserves this q to the L symmetry, whereas I guess the other one spontaneously breaks it. Okay, there's probably some nicer story to say around that type of thing, but I don't entirely know what.
Yeah. Okay, got it.
Yeah. So I mean, basically, I just want to ask how this symmetry acts in the EFT. So remember, here is the EFT that we started with. And these are the operators that vanish for a black hole. And now we just want to ask, is that special from the perspective of this symmetry? So the symmetry I showed on the previous page, so this is like one particular component. There's actually 3 of them. They're like the boosts of Euclidean ADS3. You can combine them into a vector under rotations. If you take the large R limit, they act exactly like this, which is actually just the action of an SCT. And it's not so hard to see that the free action is invariant under this transformation, but these couplings are not, okay? And so if we really take this, I don't know, it gives us, everything fits kind of neatly into our ordinary naturalness box that now when I set these green lambda L's to 0, there really is an enhanced symmetry. And we saw, what's going on is that this is some enhanced symmetry in the EFT, and this symmetry is exactly realized in the UV, which is how we always have to talk about naturalness problems, right? It's always a question about whether we can find a UV completion with some particular structure of symmetries or structure of coefficients or something. And so here's like a concrete symmetry you could ask for in the EFT that would set these things to 0. And then you can go and it turns out that the actual UV completion that is a black hole has this symmetry. Okay, so I'm cheating a little bit because I'm only keeping the leading 1 over R stuff. And what I really should do is turn back on graviton fluctuations and find a symmetry that's a symmetry of the EFT also with gravitons. And I don't know of such a symmetry. If you let me restrict to the graviton monopole sector, then I can just take the expansion in RS over R of this symmetry, and it will continue to be a symmetry of the EFT with the graviton monopole sector turned on, because that will just resum into the Schwarzschild metric. But if you really allow arbitrary fluctuations for the graviton, I don't know what the symmetry is. And that's sort of equivalent to understanding sort of back reaction effects in the UV, or understanding what the nonlinear symmetry is. So I only really know what the symmetry looks like at linear order, but of course it would be nice to know what happens more generally. Okay, so this is sort of a partial understanding of what's going on connecting IR and UV. Okay, good. So let me just mention a couple generalizations that you might be curious about. So the whole time I've been talking about scalar fields. And so you might say, all right, I don't care so much about the static response of a black hole to a scalar field. What happens if I apply an electric field or a gravitational field? Well, it turns out the equation that governs these perturbations is this Tucholsky equation. And it turns out there's yet another set of ladder-like symmetries that actually lets you transform the spin parameter that the Tucholsky equation depends on. And so once I know this whole story for scalars, I can actually use these E ladder symmetries to generate conserved charges for the spin 1 and spin 2 stories. And it ends up being exactly the same. Again, you can transform these all to like similarly special quantum mechanics problems. They all have exactly the same symmetries. And so you can understand the vanishing of gravitational electromagnetic responses really in the same language that I just told you. Another thing you might naturally ask about is, I told you at the beginning that there was something special about d equals 4. So you might say, okay, how do you see d equals 4 is special in this language? So in higher dimensions, you can write the analogous equation of motion that a scalar field satisfies in this language. Where now what appears instead of L is some L hat operator, which is L divided by d minus 3. And now what's going on is L equals 0 is still special. And now any L hat which can be connected by an integer, integer number of steps up this ladder is also special. So yeah, L equals 0 is special. There are still these ladder operators, but only specific L's are connected by a number of integer steps to L equals 0. And so only certain L hats are special. And they're exactly the ones where L hat is an integer, which are exactly the ones where the static response vanishes. And so this, this particular numerical thing, again, is natural from this point of view. Yeah, since many of the Kerr experts are here, at the IAS, let me just say a few words about Kerr. So far I've only been talking about Schwarzschild, but essentially everything is the same for Kerr. It's just the details are more complicated. There's one physics thing which is different about Kerr, which is interesting, which is that there's a zero frequency dissipative response. So what I've been talking about the whole time are conservative static responses, but at zero frequency, there's actually a dissipative response. This was explained, at least to me, by Horngsheng in this, well, in person, but he explained it to everybody else also in this nice paper. And basically what's going on is that if you were to compute these induced responses, there's a zero conservative piece, and then there's a pure imaginary dissipative piece. And you can either do it the way Horngsheng did it by matching to some outgoing boundary conditions in infinity, or you can do the matching in the EFT, which was done also by Mikhail here at the IAS. And the details of the matching are more complicated, but at the end, the static response is still zero. And you can still see there's still this ladder structure in the Kerr case, although it's a little bit more intricate. But there's this sort of interesting fact that I don't understand yet, but is kind of peculiar, which is that you can compute these like JL charges. Maybe I should have called this J instead of Q. You can compute these charges, and they happen to be exactly these dissipative responses, which sort of didn't have to happen. I can understand sort of mechanically how it happens, but it seems like there should be some physics to it. And at the very least, it seems like there should be some like elegant way of matching where you really match these conserved quantities. Okay, I know I'm a little bit over time, so let me try to just finish relatively quickly. All right, so far, everything I told you was literally at zero frequency. And what we did was look at symmetries of the zero frequency sector. But we might be interested in questions at finite frequency. And it turns out there's actually a rich structure of symmetry when you allow for finite frequency perturbations. And here's some concrete way of seeing that from some quasi-geometric point of view. So if you start from the action for a scalar in a Schwarzschild background, let's say, you can take this near zone limit, which is really sort of a small frequency limit, where you restrict to perturbations where you look at distances small compared to 1 over the frequency of the perturbation. So this is, in a sense, being near the black hole. And the way you mechanically impose this approximation is that every time you see r to the 4th over delta, you replace it by r Schwarzschild to the 4th over delta. And then you can take this effective equation of motion, which captures the small frequency dynamics of the system, and you can ask, okay, is there some effective geometry that the scalar field sees, which is not the Schwarzschild geometry, but is some geometry that it will behave exactly the same in, at least for small frequencies. And it turns out that effective geometry is exactly ADS2 process 2. Okay, so this is not the normal near horizon geometry, which would be like Rindler or something. This is a slightly different approximation, or a different approximate geometry that this scalar field behaves like it's living in. And it turns out, of course, ADS2 process 2 has a huge amount of symmetry. It's actually conformally flat, and so it has 15 conformal killing vectors. And of course, they form an SO42. So 6 of these are just the isometries of this space. The 3 rotations are not particularly exciting, but there are also 3 isometries of this ADS2 space. And it turns out these are the transformations that Mikhail and Sergey and friends used in this nice paper to extract some information, actually even about the static responses, despite the fact that you're working now at finite frequency. There's kind of an interesting fact about this, which is that because of this time-dependent factor, these symmetries actually take you out of the near zone approximation you've made. But nevertheless, they're still useful for something. So it's kind of an interesting situation where you have mapped the problem you care about to some subsector of a different problem and used the symmetries of that problem to infer something about the problem you care about. So that's kind of an interesting story. And then in addition to these isometries, there are also conformal killing vectors of this spacetime. And one of them, or 3 of them, are the symmetries that I was telling you about, which generate this ladder structure. And then there are a bunch of other ones. It turns out that because a massless scalar field, since this is a conformally flat space, and it also happens to be Ricci flat, the conformal killing vectors of a scalar in this geometry generate true symmetries of the equations of motion or even of the action. And so that's why these conformal killing symmetries are useful. And so we used, for example, this symmetry to build these d plus minus operators, but there are also a bunch of other symmetry transformations. And the nice thing about this is that actually these boost-like symmetries are actually compatible with the near zone approximation. So they're exact symmetries at small frequency, but they'll also be approximate symmetries of the full problem. But for me, conceptually, it's kind of nice that there's some at least geometric understanding of how this story I just told you and then the story of these other guys are connected together. And usually when there's something non-trivial going on, different things are aspects of some underlying structure. So it at least makes me optimistic that there's some deeper story here still to be understood. All right, yeah, so just really quick, just because Dima invited me, I felt compelled to try to phrase these things, like try to get into his world and phrase things in a language he might like. And it seems like there should be some connection of this whole story I told you to something slightly more on shell. And it seems natural to me that this statement about the vanishing of these EFT couplings should be basically related to the nice properties of the effective coupling of the Kerr black hole to gravitons or to other external particles. And I think one way of thinking about it is that when we compute these sort of effective responses, you could imagine blowing up the contact interaction that we are interested in into some sort of process like this, where a spinning black hole absorbs a graviton, turns into some J plus or minus 2 state in some internal line, and then the graviton decays away. And this is sort of some way on shell of thinking about the process that's going on when you're inducing some tidal response. And then the special properties of these 3-point couplings should presumably transform into this statement that love numbers vanish. And one reason why maybe this is interesting is that, so in d equals 4, we know that there's a sense in which high spin particles can be minimally coupled to gravity. But there's no sort of analogous statement in higher dimensions. There's no sort of unique minimal coupling vertex, but possibly the vanishing of these static responses for very particular multipoles, maybe it suggests that there is for some particular multipoles some like minimal coupling to gravity. Maybe that's an interesting fact. Okay, good. All right, so let me just summarize. Okay, so the zeroth order thing I told you about is that static black hole perturbations have a lot of symmetry, and I have, given you one way to use this symmetry to understand the vanishing of love numbers and sort of explained what these love numbers are or mean. And concretely, to me, the nicest way of phrasing this story is to say that these sort of ladder-like symmetries let us construct charges that connect different asymptotic regimes of solutions. And then there's still this kind of mysterious fact that if you actually evaluate the values of these charges in the Kerr case, they're literally the dissipative response coefficients. And even if you do this at finite frequency in Schwarzschild, you find the same, that these charges are the dissipative response of black holes. Okay, so that's a little mysterious, and I would like to understand that a bit better. So I've told you, there's this naturalness way of thinking about things, which at least motivated me. And understanding the way that these symmetries descend from the UV and act in the EFT at least makes it seem to fit in our ordinary naturalness box. But there are still some things to be understood a bit better about that story. And away from omega equals 0, so I focused on the omega equals 0 story, but away from omega equals 0, there seems to be kind of a rich structure of symmetries. And the obvious, most natural and probably most interesting question is this whole story I told you a manifestation of something a bit deeper in GR? So here I've been telling you about something very special. I've been talking about linear perturbations around the black hole background. That problem has a lot of symmetry. But you might ask, is there really some nonlinear symmetry of GR or some more nonlinear story that this is an instantiation or manifestation of? And I think that's, obviously, if I knew that, I would tell you it. But I think that's, the deepest, most interesting question to think about. And maybe a handle on this, or another further generalization or opening of this story, connecting it to other things, is there some way to connect this to the on-shell world? Okay, and I'll stop there. I'm happy to answer any questions.
Thank you very much, Austin, for a beautiful talk. We asked a lot of questions during the talk, but are there any questions now? Maybe the questions should be for the non-locals, because we will have an opportunity in 15 minutes to grill Austin locally. Any non-local questions? All right, if there are no non-local questions, maybe I will. Maybe I'll just ask one local question. Do you think there are other implications of even the sort of symmetries you understand beyond that just some coefficients are zero? Like, can you find relations between a bunch of the other? I mean, are there many more consequences of these symmetries on the structure of the effective field theory?
My expectation would be yes, but I don't know in detail. I mean, one indication that there should be more to the story is precisely this thing that like these dissipative responses are charges, which is something about the finite frequency. I mean, it's really something about the dissipative EFT. And actually that would be very interesting because the structure of dissipative effects in the EFT is not particularly well controlled. And so if there are really some symmetries of the dissipative sector, that actually would be quite helpful and useful. Yeah, aside from that, I don't know. I mean, presumably if this literally is a symmetry of the EFT, then of course it constrains a whole bunch of things.
But I meant if you just take even the action of the what looked like the conformal transformations, right?
Yes.
Just that part, and just acted on the other all the other possible terms in the expansion. What do you learn? Are these the only things that you can write down at zero frequency? Oh, maybe the guys that you wrote down are the only things you could write down at zero frequency, I guess. Is that right?
They're the only things you can write down at quadratic order at zero frequency. So there will be. So these are the only things that tell you about.
That's what I meant. Yeah. Okay. So then, but if you ask, okay, good. So you can ask for things cubic and higher order, but you would expect to see the same symmetry, no?
Yeah. I would expect so. So that, I mean, the one reason we haven't done this is I don't know exactly how to solve this problem from the GR side. You have to ask some nonlinear question in order to actually do the matching. But from the EFT point of view, yeah, of course. I mean, cubic couplings will of course be controlled by these symmetries.
Right. Okay. All right, one more opportunity for questions. Going once, going twice. All right. In that case,
everything was completely clear. Fantastic.
Yes, it was very clear indeed. All right, so let's thank Austin again for a wonderful talk.
Thanks, Austin.